So this problem explains that a 7 centimeter long wire is pulled along a U-shaped conducting rail in a perpendicular magnetic field, and it gives us that the resistance is 0.3 ohms, the length of the wire is once again 7 centimeters, the velocity is 4 meters per second, and the power dissipated in the circuit is 3.6 watts. And the problem in part A wants us to find out how big is the pulling force. So you can see I drew a picture. We've seen a few of these systems in the homework and in the book. It's a pretty simple system, just once again with that magnetic field and the velocity of the wire perpendicular. And the key thing here to note is that the velocity is constant, which means that the magnitude of our force, our magnetic force, is going to have to be equal to the magnitude of the pulling force, which has to be done essentially so you have that constant V. And that's the fact that those two are equal is going to make our equations easier to use, essentially. So part A, how big is the pulling force? So we can use the equation power equals force times velocity, which is just kind of a classic equation. And the thing that's useful here is the power dissipated is going to have to be the same power put into the system in order to keep our system in that kind of state of equilibrium, I guess. So we can still use the 3.6 watts that the problem provided us. And we of course have the velocity, and that gives us a total pulling force of 0.9 newtons. And then next, part B asks us about the magnetic field strength. So another equation we have for power is V squared over R. And you can see in this form I've written it E squared, representing that motional EMF over R. And the reason that's useful is because in the case that a conductor is moving with some velocity perpendicular to a magnetic field, we can say that motional EMF equals velocity times length times the magnetic field. That length being the length of the wire and the velocity of the wire. And so with that information, pretty much all we have to do is substitute into that original equation. The power equals E squared over R. And once you get that, you get power equals V squared times L squared times B squared over R. And I also noted that also equals what we were dealing with in the previous part, force pull times velocity. So at this stage, there's a few different paths you can take because we have a lot of information. This one might even be easier. You could do it the way that just showed up, where you're using the two equations on the left and rearranging to solve for B. Or what I did was I used the two equations on the right and then rearranged for B. But like I said, we have a lot of information right now, so you can do whichever one you prefer. Once you rearrange for B, you just plug in your numbers, remembering to convert to the correct units, and you get a total magnetic field of 3.71 Tesla. So that's the end of this problem. I think that overall it's not too bad. A key thing is just remembering your equations and remembering when they're applicable. But other than that, yeah, it's not too bad of a problem. Yeah, that's it. Thank you for listening.